Okay, in this lecture, we're going to introduce the second law of thermodynamics, and we're going to introduce the concepts of heat engine, refrigerator, and heat pump. We are also going to talk about irreversibilities. One way to put it, we can say second law of thermodynamics is about impossible directions of energy conversion or possible directions of energy conversion. Let's take a look and see what direction of energy conversion is possible and what is not possible. Here we have mechanical energy versus thermal energy. Let's see on the left-hand side, we have this container that has a certain fluid. Let's say it's a liquid, it's a water liquid in it, and we can put a steering wheel or pedal wheel in it, and through a shaft we can deliver some work into this liquid system. And if we say we put in, we add the 50 joule of mechanical work into the system, we will imagine that the liquid will get stirred, and then there will be a swirl in the fluid. And after the delivery of the work, when we let everything settle, eventually the liquid will stop swirling, and all that mechanical energy will become thermal energy. So we see that this is a possible direction of energy conversion in which mechanical energy can directly at 100% efficiency convert to thermal energy. Now in contrast, let's see if the opposite direction of energy conversion is possible. Imagine this liquid that just received the work done by the pedal wheel, whose internal energy has increased by 50 joule. Let's imagine this, let the system give up that 50 joule energy. I'm missing a unit here, 50 joule of energy. Let's say we let this process give out that energy in 50 joule. We know from our experience that 50 joule of energy, if it gets converted to work, it's impossible to convert that thermal energy back to mechanical energy at 100% efficiency. We know it's possible to convert some of the thermal energy back to work or to mechanical energy, but not at 100% efficiency. So here we see there are certain directions of energy conversion that are possible, and there are certain certain directions of energy conversion that are not possible. We talked about the energy conversion directions. Energy flow, just thermal energy flow, can only happen from a high temperature place to a low temperature place. We know that from our experience as well. We have never seen the thermal energy from snow transferred to the surrounding warm air. What we see is thermal energy from warm air transfers to cold snow. So there's another way of looking at this problem. Thermal energy only flows from high temperature place to low temperature place. Okay, it's based on these observations of energy conversion directions and energy transfer directions, we can introduce the second law of thermodynamics. It tells us what is a impossible process, what is a process that may satisfy the first law of thermodynamics, but it's not possible. So we need to have another law to tell us what's possible, what's not possible, and that law is the second law. You may already know that there are many different ways you can state the second law of thermodynamics. If they are telling the truth, they should be all equivalent. One of the most famous second law of thermodynamics statements is the Kelvin-Planck statement. And this statement is related to the heat engines. This statement says it is impossible to construct a device that operates on a cycle, and the sole effect of this cycle is to receive heat from a single reservoir and convert the heat to work. The device that operates on a cycle and converts thermal energy to work is a heat engine. And let's see what a heat engine is and whether and how the Kelvin-Planck statement is applied to the heat engine. Okay, a heat engine is a device that operates on a cycle. In other words, we can think of the heat engine as a control volume. Its sole purpose, and this heat engine operates on a steady flow process or a cycle. The sole purpose for this heat engine to exist is to input energy, to take in thermal energy, and outputs work. And in a moment, we'll know that the heat engine also, in addition to outputting mechanical work, it also needs to dump some so-called waste heat to the environment as well. And in heat engine definition, we have to define something called a thermal energy reservoir. A thermal energy reservoir is a body of matter that absorbs or releases thermal energy without changing its own temperature. So this must be a massive body that can do this. Otherwise, imagine a small thing will change its temperature once releasing or absorbing thermal energy. An example of a thermal energy reservoir is the atmosphere. For example, it's a massive body of air, and it can absorb large amount of thermal energy without changing its temperature. Another thermal energy reservoir example is the ocean. It's even a bigger thermal energy reservoir than the atmosphere. It can absorb and release energy without changing its temperature significantly. Okay, so we have defined the heat engine, and based on the Kelvin-Planck statement, a heat engine has to work with more than one thermal energy reservoir or heat reservoir in order for it to work. Why? Let's take a look at this diagram. Here we have a heat reservoir. It's a body of mass that provides thermal energy to the heat engine, and the heat engine operates on a cycle, and it outputs work. So in essence, the heat engine is a control volume, and it operates on a steady flow process. So you look from the outside of the heat engine. What you see is you have a steady stream of thermal energy that flows into the heat engine, and you have a steady stream of work that comes out of the heat engine. And based on the energy conservation principle, we know for a steady flow process to happen like this, then QHE, this QHE, the Q heat engine in, must be equal to the work heat engine out. This is based on energy balance principle. And immediately we see this is impossible, because we have just recognized that thermal energy cannot be converted to mechanical energy or work at 100% efficiency. And the Kelvin-Planck statement of second law of thermodynamics simply states that fact. All right, because of the recognition of the second law of thermodynamics through the Kelvin-Planck statement, we know that the heat engines must work between two reservoirs, at least two reservoirs, in most cases two reservoirs. The classic cycles all have heat engines work in between two reservoirs. One hot reservoir, another is a cold reservoir. So the heat engine works in a cyclic manner. It works in a cycle, and from the outside of the heat engine, the heat engine looks like a control volume. Its only effect is to take in heat from the hot reservoir and outputs some work to do work. In the meantime, it dumps some so-called waste heat to a cold reservoir. Therefore, we can infer that if we want to use thermal energy to do work, to produce work, then we need two thermal energy reservoirs. We need temperature difference. if there's no temperature difference, if everything is as warm or as cold, then there will be no potential to do work, because there's no such a thing that can get thermal energy from a single reservoir and converts that thermal energy to work based on the Kelvin-Planck statement. Now we will see this in the discussion of irreversibility. For heat engine, it is the temperature difference, or rather the potential for thermal energy to move. It's that potential, it's that natural potential that provides the opportunity for the heat engine to convert thermal energy to work. So without temperature difference, heat engines would not be useful. Okay, thermal efficiency. Thermal efficiency is a property of a heat engine. Thermal efficiency is defined as the desired output divided by the required input for the heat engine. As we know, the work is the desired output, and the thermal energy input from the high temperature reservoir is the required input. And naturally, we can apply the first law of thermodynamics, and we can see that the thermal efficiency of a heat engine is defined as such. Here is an example of calculating thermal efficiency of an automobile engine. Here are the conditions, and here's the analysis. We know the fuel consumption or the rate of a fuel consumption, and we know the power output from the heat engine. We also know the so-called heating value of the fuel, and then the energy input to the heat engine is actually the heating value or the energy contained in the fuel that goes into the heat engine, and the energy output is the work. The desired output is the 60 kilowatt power output, and the required input is the heating value of the fuel multiplied by the mass flow rate of the fuel. So we can get to the answer that way. So we can get the answer by dividing the power output by the rate of heating value input into the fuel's heating value input into the heat engine. And this is the detailed calculation. All right, we also mentioned earlier, which we all recognize, thermal energy does not flow from a cold place to a hot place naturally. And that leads to the so-called Clausius statement, which is applied to the refrigerator or the heat pump. Okay, the Clausius statement basically tells us if you want to move thermal energy from a low temperature place to a high temperature place, then you have to do some work, provide some mechanical work. Otherwise, it's impossible. Okay, there's some difference between refrigerators and heat pumps. They are essentially the same thing. They consume work, mechanical work, and then they move thermal energy from a low temperature place to a high temperature place. So technically, they're the same, but they're different from a purpose point of view. For refrigerators, what we care is the amount of heat that they take away from the low temperature place. For heat pumps, what we care about is the amount of thermal energy that they bring into the high temperature place from the low temperature place. For refrigerators and heat pumps, we do not use the term efficiency to describe how efficient they are. Rather, we use the so-called coefficient of performance to describe the efficiency of these devices. Again, the definition of a coefficient of performance follows the general principle of efficiency definition, which is the ratio of the desired output or the desired outcome divided by the required input. For refrigerators, since the desired outcome is the cooling effect, so we divide the cooling effect by the required input, which is the work input into the refrigerator. For heat pumps, the desired outcome is the heating effect. So the coefficient of performance for heat pumps is defined as the ratio of the heating effect divided by the work input. Okay, here is an example of a household refrigerator. We know the power of the power input of this refrigerator, and we know the COP, the coefficient of performance, and we have a task for the refrigerator. We know how much cooling the refrigerator needs to provide by moving or by taking away thermal energy from 5 watermelons, and we know the mass of these watermelons, and we know how much cooling is required from the watermelons. And by assuming that the watermelons are essentially water, we know the specific heat of the system, which is the 5 watermelons that needs to be cooled from 20 degrees to 8 degrees Celsius. So here the system of concern is the 5 watermelons, and we can find out how much energy needs to be removed, or how much internal energy needs to be reduced from our system by calculating this. Let's see. This is the amount of energy that needs to be removed from our system, our watermelon system, and that is the desired cooling effect from a refrigeration point of view. And because we know all right, let me correct myself. So this is the amount of heat that needs to be removed from the low temperature place, and from the power input to the refrigerator and the coefficient of performance, we know the rate of energy removal, or the cooling effect from our system, the system being the watermelons. Then we can divide the amount of heat that needs to be removed by the rate of heat that can be removed from the watermelons. So we have the time. This is time. So time is equal to the amount of energy needs to be removed divided by the rate of energy removal. Then we have this time that it takes for the heat to be removed from the watermelon. Okay, let me just add one word. So here in this problem, we apply the concept of systems to this cold place, or rather the cold place or watermelons. And we apply this analysis to this watermelon system, and we use a device which is the refrigerator to take heat from this system. All right, before we finish, let's quickly go over a couple of concepts in the heat engine, refrigerator, and the heat pump analysis. So we talked about the heat reservoir, or thermal energy reservoirs. You may ask yourself a question: what is the specific heat of a heat reservoir? The answer is infinity. Another good question to ask yourself is, what's the range of values that you can get for coefficient of performance? It's easy to see that the thermal energy efficiency of a heat engine can only be up to 1. Actual heat engines, their thermal efficiency are much less than 1. But what about the coefficient of performance? And that depends on whether you're talking about coefficient of performance for a refrigerator or for a heat pump. And one thing you can remember is that for heat pumps, the coefficient of performance is always greater than 1.